So, welcome everyone to another live stream um, for the Mathematics Academy. Today we will be going over functions. So, I'll begin very shortly. So, I think I can begin. So, yep. So first, when covering functions, we need to understand what a one-to-one function is. So firstly, a function is something like f of x, which takes an input x and outputs something else. So in this case, the function takes a value for x and doubles it by multiplying it by 2. There are several things we need to know about functions. Firstly, there's a certain type of functions called one-to-one functions. One-to-one function. Now, what are these functions? Well, the name says it. It's functions that take in one input, so one value of x, and give out one output. So what do I mean by this, for example? Well, one example we can look at is the function y equals x. This function, for every value of x, I only get out one value of y. For example, when x is equal to 1, y is equal to 1. And I can never get 1 from any other value of y, from any other value of x. So if y is 1, x has to be 1. And similarly, when I plug in 1, I cannot get any other value of x. When I plug in 1 for x, I cannot get any other value of y. This is a one-to-one function. What's an example of a function that's not one-to-one? An example of that is the function y squared equals x. Why? Well, it's because when I plug in x equals 1, yes, it's true that y can be 1, because 1 squared is 1, but it's also true that y can be minus 1, because minus 1 squared is also 1. And so if we plotted this function over here, like this, when we plug in the value of 1 for x, we get out two values of y, namely plus 1 and minus 1. So in fact, this curve over here actually looks like this. And so one way to test if a function is one-to-one or not is to use something called the vertical line test. So you draw vertical lines throughout the function, like in this case. So you draw a vertical line like this. And if any vertical line passes through the curve twice, that means for one value of x, so x value, there are two values of y. So this doesn't have to be the case all of the time. If this is the case even once, so if you have a curve where drawing a particular vertical line gives you two intersection points with the curve, then that's not a one-to-one function. All right. So the next thing we need to cover is something called many-to-one, and it's a very similar idea as well. So many-to-one function. So a many-to-one function is a function which can give you the same value of y for many values of x. So many values of x can give the same value of y. Now, what's an example for this? Well, an example is just the opposite of what we had above. So the function y equals x squared. When x is equal to 1, y is equal to 1. And when x is equal to minus 1, y is also equal to minus 1. Or y is also equal to 1, sorry. And so that means that two values of x gave us the same value of y. And in this case, when we draw the curve, we get this. So this is, of course, the graph of a parabola. And it's many to one because there's more than one value of x which gives you the same value of y. In this case, the point -1, 1, and the point 1, 1, they both have the same y coordinate. And so the test we can use here is something called the horizontal line test, where you draw a horizontal line, and if any horizontal line cuts the curve at 2 points, that means that there are two separate x values which give the same y value. And so in that case, the curve is many to 1, or the function is many to 1. Okay, so now we need to cover something called the domain and range of a function. So the domain and range. The domain is a function. The domain of a function is the set of values of x, set of values of x that you are allowed to input. You are allowed to input. So let's go over some examples. So for example, the function y equals x. Here you can input any value of x. You can input -1, you can input 1/2, you can input pi, you can input anything. Are all allowed. However, if we look at a function like y equals 1 over x, then yes, you can input 1 and 3 and pi squared over 6. All of that is allowed, but you cannot input 0. So 0 is not allowed. Why? Because if you plugged in 0, you would get y is equal to 1 over 0, which is of course an asymptote, and y doesn't reach that value. Okay, so you can't plug in the value x equals 0. So that's the domain of a function. So we can take another example. For example, let's look at the function y equals 1 over x plus 2. Let's think about what the domain of that function is. Well, every value of x is allowed. So if I plug in 3, for example, y is just equal to 1 over 3 plus 2, which is 1/5. That's a fine value. But clearly, the only value that I'm not allowed to plug in is whenever I have 1 over 0. When I have 1, and so 1 over 0 is the only value. So the value of x, which gives me 1 over 0, is the only value that's not allowed. And what's that value? Well, I can test it directly. I just take this denominator and set it equal to 0 in order to find the value, or values in some cases, of x that give us 1 over 0 for y. And in this case, it's -2. So we say that the domain of y is all values of x except x equals -2. And now another way to write this is just to say that x is, x goes from negative infinity to 2, and then from 2 to infinity. So it skips the, from negative to infinity to -2, and then from -2 to infinity. It skips the value of -2 in the middle. Because if we wanted to include the value of -2, we would have something like this: negative infinity to -2, and then we would have square brackets. Square brackets means the value of -2 itself is also allowed. And now you might ask, why is there a regular bracket rather than a square bracket next to the negative infinity? Well, it's because, of course, we can't plug in negative infinity itself. So that's also a value that's not allowed. Okay, now let's move on to the range. So the range is kind of like the opposite of the domain. So the range of a function is all of the is the set of all outputs of the function, rather than the set of all allowed inputs. It's the set of all allowed, or just the set of all outputs of the function. So again, if we go back to the function y equals x, well, clearly I get every value of y, right? Even if you graph the function, this is what the graph looks like. Every value of y on the y-axis here is matched by some value of y on the curve. So in this case, the range of this function, y equals x, is just all of the real values, so all of the real numbers. So all of the decimal numbers, basically. And so the range in this case, we would say, again, using the notation we introduced above, is just from negative infinity to infinity, like this. Okay, so let's look at a different function. If you look at the function y equals x squared, for example, well, that's very different, because if you graph this function, you see that it's never negative. All of the values of y which are negative do not have a corresponding point on the curve. The only y values which have a corresponding point on the curve, like this, are the values for which y is greater than or equal to 0. So when y is 0, yes, there's a point on the curve which has y equals 0. When y is 1, when y is 2, and so on. But when y is negative 1, you can even try this. There's no real value of x, so no real number, decimal number, which gives you negative 1 when you square it, and so there's no value of x on this curve such that the y coordinate is -1. And so all of the negative numbers, including, by the way, negative 1/2, negative 0.001, and so on, do not fall in the range of this function y equals x squared. It's only the values from 0 to infinity are in the range. And remember, 0 is also included in the range, and so if we were going to write the range, we would write it like this. So 0 is included, therefore we use square brackets, and then we do comma to infinity, and then just regular brackets. Okay. Now, if we want, now we move on to solving functions. Actually, before we do that, let me introduce a few other things. So before we look into how we can find the range, there's another way we can think about functions, or we can write functions. So a function, f, we can write it as, for example, f of x equals x squared, and that's just exactly the same as saying y equals x squared. The difference between the two is actually the difference between thinking about if you're going to graph the curve. So this is if you're going to graph it, and this is only if you're thinking of it as a function. So in fact, if you want to graph the function f of x equals x squared, then you let y equal f of x, and then you graph it, and then you get this. So you get the normal curve y equals x squared, but it's just a matter of notation, and to be precise, we say that when we write y equals x squared, then we're talking about the graph, or the curve, and when we say f of x equals x squared, then we're talking about the function. But just from now on, you can use y and f of x, or think of them as the same thing. Okay, and so another way to write this f of x equals x squared is to say that f takes a value of x and maps it to x squared, right? And that's simple. Just takes a value of x and maps it to x squared. For example, f of x equals 1 over x. We can write that as f takes a value of x and maps it to 1 over x. Okay. Now let's think about how we can find the range for different types of functions. So I already introduced the function f of x equals x squared and said that it has a range of 0 to infinity. Let's look at other quadratic functions. So let's look at f of x equals x squared plus 1. Well, if we plot some of the points, when x is equal to 0, f of x, or y, is equal to 1, and then when x is equal to 1, y is equal to 2. When x is equal to 3, y is equal to, when x is equal to 2, y is equal to 5. So that's up here. And by the way, we get the same values, of course, for just negative x, because squaring a negative number gives the same result as squaring the positive of that same number. And so you'll also get the same, so just the reflection of the points on the negative x-axis. And so the curve that you get is also a parabola, of course, like this. But the range is different here. So what's the range in this case? Well, remember, in order to think about what the range is, we need to think about what are the values of y that we get on this curve. So what are the y coordinates of the points on this curve? Well, 0 is clearly not a y coordinate on of any point on the curve. So 0 will not be in our range. However, 1 is a y coordinate, right? Because the point 0, 1 with a y coordinate 1 lies on the curve, and so that will be in our range. And so will any other point above 1. And in fact, any point strictly below 1 will not be on the curve. And so our range in this case is 1, infinity, like this. Okay, let's take another example. Let's take y equals x minus 1 squared plus 1. So this is slightly more complicated, but let's think about it anyway. Okay. So again, in order to get an idea of what the range of the curve in this case is, we need to think about graphing it. So let's try a few values. When we plug in x equals 0, we get 0 minus 1 squared, which is the same as just minus 1 squared, which is the same as 1 squared, which is just 1. And then we add 1 to that. That gives us 2. So when we plug in 0, we get 2. Okay? And when we plug in 1, we get 1 minus 1 squared. That's just 0 squared, which is 0. And we add 1, so that gives us 1. Okay? And then when we plug in 2, we get 2 minus 1 squared, which is 1 squared, which is 1, plus 1, that's 2. Okay. And so on. And we can see here again, this is a quadratic curve, so we'll probably get something like this. Right? With this being the minimum point, because we can see that when we plugged in 1, the squared part went to 0. And the smallest a square can ever be is 0. It can't be negative, right? Because otherwise we are dealing with complex numbers and things like that. Okay. So this is what the curve looks like. And so let's think about the range in this case. Okay. So in this case, again, when we think about what the y coordinates of the points on this curve are, well, the y coordinate of 1 does exist on this curve, on a point on this curve, for a point on this curve, the point 1, 1. And so does every value of y above 1, right? So all of the values of y from 1 to infinity are in the range. In fact, any value strictly below 1 is not in the range again, because you can also use the horizontal line test here. If you draw a horizontal line below 1, it will not intersect the curve, and therefore that value of y will not be in the range. And so in this case, the range again is just all of the values of x greater than or equal to 1, the values of y, sorry, greater than or equal to 1, which is 1 infinity. And so it's interesting here that the range was the same for both of these curves. And in fact, this curve, as we will see later, by the way, is just a translation by 1 of the curve above. Translation to the right by 1. Okay, let's look at another curve very quickly. So let's look at the curve y equals x squared minus 2x. So this one is slightly more complicated, but what we can do is, when we're faced with a curve like this, we can try to do what's called completing the square. So it's much easier to deal with a curve if you have it in the form of like x minus a squared plus b. This is far easier because you then know that the minimum value will be when this is 0, right? Because the minimum value that this can ever be is 0, and this will be 0 when x minus a is 0, which is when x equals a, and that's what we saw above here. The minimum value here happened when x equals 1, and the minimum value above here happened when x equals 0, because here we had x minus 0, and here we had x minus 1. Okay, so we want to get this curve, or this function, to be in this form. How do we do that? Well, we need to think back to what this means. So this x minus a squared plus b, that's the same as x squared minus 2ax plus a squared plus b. Okay, so I need to match this curve over here with this curve over here. So for example, I can see that the x squareds already match. They're exactly the same. The negative 2x is almost the same as negative 2ax. In fact, the only difference is this factor of a here. And so that tells me that I need to choose a to be 1. Okay? But once I have a equals 1, then I have 1 squared here, but I only have 0 here. And so I need to choose b such that a squared plus b is 0 as well. And so b needs to be minus 1. So let's in fact try this. So if I let y equal x minus a squared plus b, which is the same as x minus 1 squared minus 1, then if I expand this out, so by the way, hopefully you saw how expanding x minus a squared worked, but I'll just show you here. You can just write them out like this, and soon enough you'll see that it's just much easier to think about it this way. You do this, that's x squared, and then you do this, which is minus x. You do this, which is minus x again, and you do this, which gives you plus 1, and then you have the minus 1 factor, minus 1 term, and so you get x squared minus 2x, and this 1 and the minus 1 cancel, and so you just get x squared minus 2x, which is indeed what we had above. Right, and so that tells us that this curve over here is equivalent to this curve over here. Okay, but this curve over here is exactly the same as the one we drew above, except there's one difference, which is that above we had plus 1, and down here we have minus 1. So if we sketch the curve in this case, we know that the minimum value will happen when x equals 1, right? Because this is x minus 1 squared, and so this term over here is smallest when it's 0, and that happens when x equals 1. But when x equals 1, the entire curve, right, the x minus 1 squared minus 1 is minus 1. And so you can even try to plot values, and I encourage you to do this, and you'll see that when x equals 1, y goes to minus 1, and so we have this point over here. And then when x equals 2, y is equal to 0, and so on both sides of the point 1, the point minus 1, sorry, the point 1 minus 1. And so you get a parabola like this. So this is the y equals f of x parabola for this function that we have here. Okay, and so let's think about the range of this function in this case. Well, again, what we need to do, again, and we can just use the horizontal line test. So for any horizontal line below y equals minus 1, we do not get any intersections with the curve, and so any value of y less than minus 1 will not be in our range. Minus 1 is in our range because we do have a point for that, namely the point 1 minus 1, and so is any point above minus 1. And so our range is minus 1 to infinity. And now let me show you what it will be in general. So suppose you had a curve. Actually, what would happen? Let's think about what would happen if we multiplied this curve over here by 2, like this. Would that change our range? Well, yes, it would, right? It would just multiply our range by, actually, better to think about this later. So let's skip this for now. Let's not think about this now. What we need to think about instead is that this completing the square trick that we used here in order to simplify our task of finding the range, we can do in general. In the case we had above, we were very lucky because we had a coefficient, so the number here was 1. And so that made it simpler to use completing the square because we only needed to write it in this form. But what if the number here was not 1, but maybe it was 2 or something like that, like y equals 2x squared minus 4x? Well, in this case, we would need to use an expanded version of this, where we have a times x minus b squared plus c. So this is slightly more complicated, but it's just the same, because now, again, we need to do the matching trick, where we expand this and try to match terms together from both of these. So how do we expand this? Well, we have a, so let's expand the squared term first. We can just expand that as x squared minus 2bx. So it's 2 times this times this. This is minus b and this is x, which gives us minus bx, but then we multiply by 2. And then we add the squared of this term, and this term is minus b, so when we square it, we just get b squared. The minus goes away, and so we have b squared over here, and then we add c. And then that gives us ax squared minus 2abx plus ab squared plus c. And now this looks way too complicated. And so in fact, you might feel like, it's better not to use this method, and I would agree. The better method to use is to do it directly. So you start with the curve that you have, which is 2x squared minus 4x, and then you force it to have an x coefficient of 1 exactly. So what that means is you pull out the 2. You pull out the 2 so that you have x squared minus 2x. And once you have x squared minus 2x, you can complete the square on that as we are used to. And above we saw that x squared minus 2x is x minus 1 squared minus 1, right? So completing the square is basically trying to get rid of the term which only has x on its own, because that complicates things and doesn't allow us to see clearly where the minimum point is. And so if we complete the square on this part, which gives us x minus 1 squared minus 1 inside the brackets with the 2 factor on the outside, okay, then that's the expression we have so far. And then now we can distribute everything. So we can just multiply here and multiply here so that we get 2 times x minus 1 squared minus 2. Okay, and then now it's much easier to think about the range of the second curve, this curve which we've multiplied by 2, because again we know that the minimum will happen when this is 0, which happens when x equals 1. And so the minimum will be at x equals 1 somewhere. And when x equals 1, we see that we get 1 minus 1 squared, which is 0, multiplied by 2, that's also 0, but then we subtract 2, and so we get minus 2. And then we get some other things. We know it will be something like this. We don't really need to concern ourselves with what the other points are. We just need to think about the minimum, as we've gotten used to by now. And then again, we try the horizontal line test. So we draw horizontal lines, and we see that for any value of y less than minus 2, we don't get any intersections, but for minus 2 and above, we do. And so the range is from minus 2 to infinity, which is, in fact, this value here, which we get all of the time. So every single time, we would get the value that was here to be that part of our range. And so in general, what we have is if y is equal to a times x minus b squared plus c, if a is greater than 0, then the range is from c to infinity, and if a is less than 0, then the range is from negative infinity to c. And of course, if a is equal to 0, then we lose this entire term, and so the range is only c, right? Because we'll only get the curve y equals c, which is just a horizontal line at y equals c. Okay, so that's it in terms of finding the range. Now there are several other things that are useful to know, and I'll go through these briefly. So how can we solve functions? So suppose we had f of x is equal to x squared, and we wanted to, find f of 2, for example. What does that mean? Well, it just basically means plug in 2 for x, and so that's just 2 squared, which is 4. Okay, now suppose we have two functions, f of x equals x squared, and g of x equals 2x. So notice the g that I added here, that's just another way of, just to show that this is a different function. I can't use f of x again, because I might get confused about which function I'm talking about. Now, if I do f of 2, I still get 2 squared, and if I do g of 2, I get 2 times 2, which is 4. Okay, that's fine. This is also 4, but that's not the point. The point is that I can plug in anything to x in both cases, and all I need to do is replace the x on the right-hand side with whatever I plugged in here. So if I plug in a for x, then it's just a squared, and if I plug in a for x in g, then it's just 2a. In fact, I can also plug in functions for x. So I can plug in g of x into x in f. So what does this mean? I can do f of g of x. This is, so what does it mean to do this? It means that wherever I see an x in the right-hand side here, I just replace it with whatever I've replaced x with, which in this case is g of x. So in this case, instead of x squared, I need to have g of x squared. But what is g of x? Well, it's 2x, right? So I need to replace g of x with 2x, so that I have 2x all squared, which is 2 squared times x squared, which is 4x squared. And similarly, I can do g of f of x. All I need to do is go to g, and wherever I see an x, I replace it with whatever I've replaced x with, which in this case is f of x. And so I have 2, not x, but 2f of x. But f of x is x squared, and so I get 2x squared. Okay, so these are what's called composite functions. So you're composing two functions together, you're putting them together. Composing functions together. And f of g of x, for example, which you can also write as f circle g of x, is a composite function. Now, there are only a very few more things that we need to go over, which is inverse functions. So we've covered composite functions, and there are actually functions which, so for example, suppose I have f of x equals x squared. There is a function g of x such that if I put in f of x to it, I get out back x. So what does this mean? This g over here is doing the opposite of what f does. What is f? Remember, think of functions as something that takes a number in and gives a number out. So f takes x in and it gives out some number, and then g takes that second number in and gives out back x. So it does the opposite of what f does. It's the inverse of f. So g is called the inverse of f. Now, how do you find this inverse? Well, there's a very simple way of finding the inverse. First, you start by looking at your function again. You say, okay, so this is the function that I need to find the inverse of. The function is f of x equals x squared. So first, I write it in terms of y's and x's, because that simplifies everything in terms of the algebra. Okay, so I haven't done very much here. I've just replaced f of x with y. And now every time I see a y, I replace it with x. And every time I see an x, I replace it with y. Okay, so I have a y here, that gives me x. And here I have an x, so that gives me y, but that x was squared, and so this y is squared. And then what I do from now on is I solve for y. So y now is equal to plus or minus the square root of x, right? Let's not forget the plus or minus. Actually, let's assume that it's strictly plus. So I might have told you here that f of x is greater than or equal to 0, and so it can't be negative, and so we need to keep it as plus. Okay. And now, what do I do with this expression now? Well, this is actually my inverse. So my inverse function, which is actually written like this, f inverse of x, not to be confused with 1 over f of x, is equal to the square root of x. And now think about this. Does this make sense? So what this is telling me is that if I take a value of x, and then I square it through f of x, and then I square root it through f inverse of x, I get back x, and that makes sense because square rooting is the opposite of squaring, right? And so it's clear that f inverse of f of x is indeed x, and you can verify that by, again, remember, plugging in as we are used to. So what's f inverse of f of x? Remember what we covered in composite functions above. Whatever you see an x, you replace it with whatever you replaced x with, which in this case is f of x. And so we replace x in square root of x with f of x, and so we get square root of f of x. But what's f of x? Well, f of x is x squared, right? And so we have square root of x squared, which we can just think of simply as x. Kind of. Not exactly, but it is x, basically. If x was positive or non-negative. Okay, so that's inverse functions. Now there's one last thing that we need to cover, which we briefly went over above. There's functions. And that's transformations. So when we saw when we had the function y equals x squared, we saw that that looked like a parabola, like this. And then we saw later on that when we replaced it with x minus 1 squared, that it got shifted to the right by 1. So we got something like this, where the function was shifted to the right by 1. And what did we do in order to shift it to the right by 1? Well, we just replaced x with x minus 1. And so in fact, in general, if you have a function f of x and then you do f of x minus a, you shift to the right by a. And so for example, if you have a function f of x and then you want to understand how that relates to the function f of x plus 2, well, f of x plus 2 is the same as f of x minus 2. Remember, you need to have a minus here. That's very crucial. And so f of x minus 2 is just, that means just shifting to the right by minus 2. And so that's just following the rule above here. But shifting to the right by minus 2 is the same as shifting to the left by 2. And so shift to the left by 2. And now shifting to the left and to the right is what you do to the x-axis part. You can do a similar thing to the y-axis part. So if you have f of x and f of x plus a, so keep in mind that this plus a is outside of the bracket, so you don't actually input it into f with x. So if I wanted to plug in 1, I would plug in 1 first and then add a, rather than adding a first and then plugging all of that into f. Okay? And so what that does is it shifts f of x up by a. And it's clear why that's the case, because if I have the function y equals x squared, or the curve y equals x squared, and I want to think about the curve y equals x squared plus 1, well, that's just the same as y equals x squared, but just shifted up by 1. So this is y equals x, and this one here is y equals x, oh sorry, this one's x squared, and this one's x squared plus 1. Alright, and now these are two transformations that we've seen. So we've seen f of x minus a, and we've seen f of x plus a on the outside, and this is minus a on the inside. Now another one is f of minus x, and what that does is it's a reflection of f of x in the y-axis. So for example, if I have the function y equals x, which is a simple straight line graph, right, this, then if I replace x with minus x, which is what this is telling me to do, so in other words, I have y equals minus x, well then I have the reflection of this in the y-axis. So if you think about reflecting this, which gives us this point, for example, and then if you reflect this in the y-axis, think of this as a mirror over here, then you get this point, and you in fact get this line over here, which makes sense because that's what the line y equals minus x is. It's just a diagonal line, the other diagonal of this plane, basically. And it's the reflection of the line y equals x in the y-axis. And the last one again, now this is again thinking about reflecting points horizontally, right? So basically reflecting points along the x-axis, even though we're reflecting it in the y-axis. So it's still y-axis. So the mirror in this case is the y-axis. We can now consider what the mirror, what would happen if we thought of the mirror as being the x-axis. Well, in this case, we get minus f of x, but the minus is on the outside. So minus f of x is a reflection in the x-axis. And so if I, for example, had the curve y equals x squared, then if I just put a minus in front of it, so that's just multiplying it by a minus, basically. So just putting a minus in front. It's not replacing x with minus x or anything like that. Then the first curve would be just the normal y equals x squared, which we're used to. And the second one would be minus x squared, which would be taking every value here and making it negative. And so we get a curve like this, which is exactly what this looks like. And so it makes sense that this is a reflection in the x-axis. And so these are the four transformations that we've covered. We've covered f of x minus a, we've covered f of x plus a, we've covered f of minus x, and we've covered negative f of x. And overall, we've covered one-to-one functions, many-to-one functions, domain and range. We've covered some notation. We've covered how to find the ranges for quadratic functions. We've covered solving functions. We've covered composite functions.